Okay, so for the final lecture, let's just first finish off our discussion from before about DGLAP. So we're almost there. So let me tell you the general case, at least sort of pictorially. So there's our DGLAP in our general case. Let me write that. So now, you know, I've talked about quarks emitting gluons, but there are also gluons which can emit quarks and gluons that can emit gluons. And so the bottom line is that one needs to include all of those, and therefore the evolution of these things mixes all of that together. So let me write that and then give you the picture. One would end up with something like this. Squared. I'm going to do it the other way. And what you end up with is this. Certainly NLO. So a coupled set of equations. I've simplified by just considering one flavor of quark that one can generalize. And we're going to have the quark. I won't even put the arguments in there. But of course, I have x and q squared arguments. So yeah. So again, let me just state that. But really, we're not too interested in the precise forms of the integral and whether it's 2 pi or 3 pi. And let me just give you the picture, because that's what's really interesting here. So the mu-f squared dependence of a quark or a gluon PDF it's just given like this, right? You can emit a gluon from a quark. A gluon can split into a quark and an antiquark. Quark can split into a quark and a gluon in the same way, or a gluon can even split into gluons. And then we go there. There's the quark. There's the gluon. And so the quark PDF, what can be you know, the change in the quark PDF is given by a quark emitting a gluon and becoming a quark. Also, a gluon could split into a QQ bar and give you your quark PDF. And likewise, a gluon PDF can be given by a quark, the quark splitting to a gluon, giving you the gluon PDF, or a gluon splitting to a gluon and giving a gluon PDF. So physically, you know, the scale evolution is just given by those possible splittings. So what does that mean? Oops. So, you know, a quark Q of x1 can be produced, for example, in these sort of splittings. And this is really physically what's happening. I could have a Q with some larger x2 emitting gluon and giving you that Q of x1. So Q of x2 bigger than x1 goes to a gluon plus a Q of x1, or a gluon, again with some x2, could give you your x1 Q bar plus the Q of x1. Okay, and this will then increase the size of your Q. Okay, the quark that you actually see when you scatter off it, if it can be produced by these splittings. But of course, you can also lose, can also be lost, if you like, via same sort of splitting. So a Q of x1 could go to a Q of x3, say. And so the quark would be lost. So the general trend in the end, when the dust settles, is that as the scale increases, you get more radiation. That's really the dominant physical thing to take home. And so what this tends to do is it pushes partons to lower x. To get more and more lower x partons, carrying less momentum of the proton, because there's all of this radiation effect kind of carrying momentum away. And in addition, these sort of things generate sizable gluon and C quark, antiquark PDFs. Finally, to predict the same sort of arguments I made for the renormalization scale, one should take mu f to be of order the hard scale of the process, precisely because there was that log in q squared of mu f squared. So it's the same sort of argument. You won't have something that's sort of perturbatively stable if you don't take that. So you take that same mu f, well, let's put that in explicitly. So on the right hand side, we need to take something. Doesn't depend up to the order you calculate what you take, but does beyond that, and so you need to take a sensible value. Well, let me put it this way, sorry. So to predict to F2 measured at Q squared, it's sensible, let's say, to take mu F squared equals Q squared, which means, you know, quite a lot of radiation in principle is actually absorbed into those PDFs. And we have simply F2 of x q squared is equal to x sum of eq squared x at 1 dxi of xi. Really don't worry too much about the precise limits on the integral and all of that business. It's not too relevant for us. Really, we're just interested in the fact that F2 has a q squared dependence, right? That is precisely driven by the q squared, the mu f squared dependence of the PDFs, driven by dglap. And the final thing I'd say is that, you know, this is a genuine physical effect. This may seem a little bit kind of formal and abstract, but really it's quite straightforward in the end, the actual physics of it. So in essence, as q squared increases, the real q squared with which you're probing that proton, we have more phase space for extra radiation. So this sort of thing happens. Increase your q squared, you know, genuinely the q squared probe there, and one tends to get lots of that and all sorts of other things. And that genuinely has a physical effect. And, you know, the PDF mu f dependence, that dglap and etc., is simply a way, if you like, for theorists to keep track of that in a consistent way. But that's the physics underlying it. So let me quickly show a slide or two just to make some points there, perhaps. So yeah, let me go back a little bit. So here, first of all, we've got Bjorken scaling, and what one can see here is that this is essentially something which is proportional to F2 at a whole load of different x values, and one can see clearly it's depending on x, okay, as you can see, but one also, for fixed x values, one's looking at it versus q squared, and what you can see is that it looks pretty constant with q squared, which would be the leading order expectation, but actually it's got some scale dependence in there, very mild, and that's precisely matched by what you expect from dglap. So one really sees these things experimentally. And again, here is really seeing in some PDFs that point I've just talked about. So here are the PDFs that are a lowish scale, and one can see that you've got the gluon, you've got the valence quarks, as I sort of motivated by drawing, but also those C quarks, the strange, the charm, the bottom. And now you increase your scale, and exactly as I said, DGLAP increases all of those low X partons. And if you zoomed in there, you would see it's decreasing the high X because they're radiating away gluons and quarks via those sorts of things. And yes, the final thing I like to say there is that, you know, one dominant thing of that is that at the LHC, where you can really probe things by gluon collisions like Higgs production, this effect means that your gluon PDF is hugely bigger than, for example, what you would naively associate with the proton, the valence and the down. And you can see that here. This is just the same thing at the right-hand side, but not cheating by dividing the gluon by 10. Really get an idea for how much bigger the gluon is. That's purely this radiation effect, this DGLAP, if you like. Okay, so what about hadronic collisions? So I won't go into too much detail because it's really the same idea. The picture is much the same. So sigma pp, it's just the same sort of parton model approach, but now you've got two protons, so two PDFs. So let me write it like that. X1 mu f squared fj of x2 mu f squared, and you're going to have a sigma hat ij of x1, x2, alpha s, q squared over mu f squared, etc., etc. And so, for example, you know, Drell-Yan, which is a real classic example at the LHC, just Q lepton pair production via a leading order, just a quark and an antiquark annihilating, like so. Okay, could be an electron and a positron, or muon and anti-muon. And you just write it in that way. So there you'd have a quark PDF and an antiquark PDF, and one could just do the calculation. And so for Drell-Yan, one can do a little bit of kinematics. PA, PB, that's the quark and the antiquark, and the PL minus and the PL plus, that's the leading order parton model. Of course, one has higher order corrections as well, as I'll mention in a minute. And one could say that PA is equal to x1 times the proton momentum, proton 1 momentum even, so something like that. And PB would be x2. This is just what defines the parton model, and now that proton is going along the negative z-axis, so it would be that. And with a little bit of work, you find that ml squared, well, in particular, I leave this as an exercise, one can show that x1 equals MLL, invariant mass of the lepton pair, over root S, that's this center of mass energy, proton-proton center of mass energy, rapidity YLL, and x2 is equal to MLL over root S e to the minus rapidity YLL, where YLL is equal to 1/2 the log of the dilepton energy plus the dilepton Z momentum. It's just an experimental observable, some of you will certainly be familiar with. And so really the bottom line here is that, again, a leading order, you know, there's a simple direct relationship between lepton kinematics and the proton parton momentum fractions. Okay, so that's all there is to say, and one can therefore use this, for example, to constrain PDFs, also at the LHC. So what about beyond? This becomes more complicated. Clearly, it's higher orders, and we have the same issue with collinear singularities, right? So that NLO, for example, we've got, there's the leading order again, but we can also now have a gluon emitted from there. or a gluon being emitted from there, or those virtual corrections again, such as that one. Okay. And what happens is exactly as in DIS, we call that A and B. The initial state, collinear divergences get assigned to the PDFs in exactly the same way. One can make exactly the same argument. So it works also in the Hadron Collider case. And really, it's just the same argument. So the state of the art is n cubed LO. Very recent state of the art calculation. And so that really means something like that, or something like that. For example, that's one of many, many, many diagrams. So real tour de force calculation. Let me show that. Briefly. There we go. So that's is the Drell-Yan cross section. So this is the rapidity distribution at the top. And actually just going to n and LO there, but one can see for one thing is that the uncertainty variation band, which is just that scale variation band I talked about before, gets rather small when you go to next leading order. So we're talking about high precision, percent level precision. So I've cut off the bottom axis there, sorry, but that should be Q. So that's just the invariant mass of the dilepton system in JEV. And this is now the n cubed LO result, the ratio to the n cubed LO. So the ratio of the n LO to the n cubed LO is in the blue, for example. And don't be fooled here that the scale is rather zoomed in with respect to the top one. And what you can see is really, really small uncertainty, scale variation uncertainties, and a really nice, precise calculation. And so the bottom line again is a factorization argument, and when it goes to the Hadron Collider case. So the FQs in, for example, Drell-Yan, the quark PDF is the same object as in the DIS cross-section. It's the same thing. So even if you don't know how to calculate it, we've got a statement that it's the same thing that enters in both cases. And that's the get out here, because I've never said how we actually calculate these things. I've sort of hinted that you need some sort of model. One could in principle do it with lattice QCD, although we're way off that just yet, but it can be done. But one never has to really do that. And why do you never have to do that? Because one can fit it using that factorization. Because this is not possible, certainly using perturbation theory, because it's all down to that non-perturbative long distance binding of the quarks and gluons in the proton, and that's just not something we can get at in that way. So what you instead do is fit these PDFs to, e.g., DIS data. So one measures DIS, one has your theoretical prediction for the sub-process cross-section, one extracts the PDFs using that, and you could predict, for example, Drell-Yan. Okay, that's a little bit of a loose example. It's not really what we do these days. Actually a great deal of data, also from the LHC, and Drell-Yan is one key thing, and DIS, Drell-Yan, etc. Because what we're really interested in predicting is, of course, something beyond the standard model, or predicting the standard model so we can see if there's something beyond it, rather. I think that's a more better way to put that. So a great deal of data going into global PDF fits. And the aim is to determine them as precisely as possible. And the point is these uncertainties, they're approaching actually the percent level in terms of these sort of determinations in some cases. So we're doing pretty well, but we want to do that sort of precision physics of the LHC. And so these PDF uncertainties can really be a key element in the uncertainties for various predictions of the LHC. Certainly a limiting factor, they can be, but we have a way of dealing with them in principle. So again, let me just go back to my slides briefly and just show you an example of that. So this is a PDF fit, the recent one, MSHT20. And you know, I'm not going to read these. Just every line here is a data set that goes into the fit. So there's a lot going on, but what I've expanded at the bottom is the chi-squared per number of points in a fit using NLO theory and in a fit using NNLO theory. And we can see once you use NNLO theory for all of these processes, one gets a rather good chi-squared per number of points. I'm not absolutely perfect, but we live in an imperfect world. Certainly at a very non-trivial test, the QCD seems to be working. And one can see also that that bottom plot is entirely LHC data. So also, as I say, LHC data driving these fits. So the final caveat, that's the good news if you want, is that factorization is only rigorously proved actually for DIS and Drell-Yan. It's assumed to work. Then we've got reasons to think it probably will for other things. Jets, TT bar, etc., etc. The LHC, and you know the key point here is, by the way, you know, well, why might it not work? Well, it's because you've got two protons in the initial state. So it seems fairly potentially, it might seem to you quite straightforward that I can just sort of say that that's the same quark as it is in quark PDF as it is in the DIS. You know, why shouldn't it be? And indeed, yes, why shouldn't it be? It probably is. It should be, right? But the point is that you've got two protons now, and therefore you can also have extra QCD interactions there. And as soon as, unless you can show that those sort of cancel in some way, then, you know, that could in principle spoil a sort of factorization of that sort. One would need something which actually includes the fact that the protons themselves are talking to each other, and getting, you know, showing that is the non-trivial element of proving this sort of factorization. And the more colored particles you add into the process, the more difficult it becomes, essentially. Okay, so let's give you a little bit about jets. So just a brief sort of introduction. So again, experimentally, we said a little bit about them already. These are a collimated cluster of hadronic energy. And you often know them when you see them. But we want to be more quantitative, because, you know, that's obviously not enough to just say that. Oops. So the idea here is to have a jet algorithm. This reduces the complexity of the final state by combining a large number of final state particles into a jet. So we start with something like, you know, that looks like this, perhaps, very schematic. And this is the kind of case where you might kind of clearly say that's sort of 3 jet-like, perhaps, and you do your jet algorithm, and you end up with some jet momenta, which would look something like that. And that's the kind of thing you want to work with. So this really allows us to trace back to the hard scattering. Process, because of course that's what you measure, the left-hand side. What we predicted looks more like the right-hand side, potentially, if we don't run it through a Monte Carlo, in a way that is, or should be, insensitive to all that soft and clean irradiation I've talked about. So there's really been major advances in the recent years on this. You know, we can really do precision physics with jets, and we've got fast infrared safe algorithms. We've got substructure techniques for kind of looking within jets, for tops and Higgs and those sort of things. And we also have a next to leading order QCD calculation of the actual underlying process. I'll show you some slides on that in a second. But let me talk about the basic idea of how these things work. And I'm sticking with a sequential algorithm because that's really what's done at the LHC. There are other types out there, but I won't talk about them. So sequential algorithm. And the idea here is to map, is to give you a map from n+1 momenta to n momenta. So for example, if one had 3 particles in the final state like that, just being very schematic, one could map that, as I say, to jet 1 and a P and a jet 2 like that. And then if there are more than that, you would be iterating. So we merge these, like as I've shown above, according to how close the momenta are. And, you know, it could be that P3 in the above case is soft, and you would combine it with P1 or P2, or maybe, because these are the sort of things that will get generated in the showering. P2 is proportional, is sort of collinear to P3, and so you would combine P2 and P3. So to some extent, although that depends a little bit on the algorithm, but it's a nice way of thinking about it. One can think of this as sort of undoing parton shower, taking you back to the sort of parton level result that one would have if one just used a fixed order prediction. And that's the sort of simplifying element. So i.e., you know, that's P1 plus P2 plus P3. This takes you to a jet, P1 plus P2 plus P3, and so on. So we need a distance measure to do this. To do this, so let's do that. And then we've seen that already, as I say, in the case of this tau variable in earlier lectures, and it's sort of the same thing here. So it's just something which tells you how close do 2 particles need to be before we consider them to be part of the same jet or not. And that's just always the basic idea. So let's take a simple picture. Let's say there's just 4 particles in the event for simplicity. Then we choose, let me write it down here. We choose some distance measure delta Rij, and we order these things, these pairings by size for each pairing Ij. Okay. And let's say in this case, one can sort of see in the picture that maybe R12 would be the smallest. So we find that delta R12 is smallest. And then we say, if we want jets with R, some radius R, so there's the distance measure, greater than at R12, then we combine them. But if not, we don't, we call it two jets. So if our R there, if you like, is bigger than that distance, then we call it one jet. And to do that, we combine them. So let's do that. Let's say it is, then it will look something like this. Okay, there's 1 + 2. And now the next smallest is clearly, well, let's say it's going to be delta R43. And now if delta R43 or 34 is greater than R, then let's draw that again. There's our R. We want to call that a 3-jet event. But if F delta R34 is less than R, so in the same picture as before, but now our R is such that it's bigger than that, then that's going to become something like this. And that's going to be a 2-jet event. And really that's it. I mean, there's obviously complications, but that's the idea. So this is a simplified picture, but it gives the basic idea. Now for hadrons, so let me add in some of those complications quickly. So for hadron colliders, there is a complication, which is worth pointing out, which is that you need to include the possibility that jets can come from the initial state particles, from the beam, if you like. And that needs to be built in. So I've not talked about that yet. So in particular, something like this, QQ bar Drell-Yan again, that could be a jet. You could see that genuinely in your detector. And one needs to allow for that. It complicates things, but not too much. So at the LHC, when it's all as above, but there's one kind of broad class that we use, which is just like that above, but with a little bit more complication. And as I say, that allowance for the fact that jets can come from the beam. So this is dominant. So let me write it down. We've got a distance Dij. And we say this is the minimum. And here's the complication. Pit squared of parts on J, I, sorry, and Pjt squared of parts on J. That is the same as before. That's our distance. But we also have this beam distance as well, which is just a Pt. So that's that fact that it could come from the beam. And R is the jet radius. And delta Rij is literally just, if you curl out your detector, it would literally just be the distance between the particles in that, the actual distance, nothing more than that. So this is the rapidity separation and the phi separation. So, P equals 0 would literally just be that, because then the power goes away. But otherwise, one just weights your measure so that it's not literally just a distance in angles and rapidities. It also depends on the actual how much PT the partons have. But again, it's just the same algorithm on top of that. And these just have, there are various reasons I won't go into for why they can be more convenient. So yeah, let's say different choices. Of P favorable for different reasons. So P equals 1, we call the KT algorithm. P equals 0 is the Cambridge Arkin. And P equals -1 is the anti-KT. And the anti-KT is a very favoured one at the LHC, particularly because it gives sort of nice circular jets, and there's actually a problem precisely on that in the problems, but I won't go into that here. Let me at least give you how this works. So we work out Dij for all pairings. We find the minimum of Dij and Dib. And if it's Dij, then we've got two particles that we want to combine. So combine I and J and go to 1, go back and start again. And if it's Dib, then it's a jet and you remove it from the list. Not doing anything else with that, that's just your jet. And you stop when nothing remains. So that's the idea. And, you know, if you want to convince yourself that that makes sense, just, you know, write down a little simple example with 4 particles. Think about maybe the Cambridge Arkin, because that's the simplest, and just think about how it might work and actually do what you want. Okay, so to produce these jets at the LHC, the leading order process alone is very complicated. So it's a 2-to-2 quark-gluon scattering. So you can well imagine that that's the leading order case, that doing this at NLO or NLO even is not easy. And indeed that's the case, but it has been done. And I've got some slides on that for you to look at, probably offline. Okay, so let me jump ahead. So I wanted to say a little bit about jet properties, but I think we have no time. So I will write a line or two here and point you to where in the notes, because there is a problem on that, but maybe by going through the problem, if you have time, will allow you to understand a bit about that. But the only point is that one can look at all sorts of properties of the jets, their invariant masses, the PT they have, and this sort of thing. And I can tell you about QCD, give you some nice information, but I will skip through that for now. C notes, let me say. Let me leave that blank. Okay, let me say something a bit more broad. So let me talk about electron weak physics a little bit. Just a few sort of things. I'm not going to go into any details, but just to give you a kind of idea of how much, what we can say there. What about the rest? Clearly I've focused on QCD for reasons I'll discuss again, but clearly there's a lot beyond that. So the standard model clearly has a non-trivial, let's write it out, SU2 left cross. You learned about this in your standard model course. There's that non-trivial structure. And here is a crucial point, and this is really the basis of some really important stuff that's happening at the LHC, which is that within this gauge theory, there arise non-trivial relationships between apparently unrelated observables. So let me give an example. E.g., let's imagine we measure MZ, MW, GF, MZ and MW, or MW, I'll say in a minute, we can actually do it, the LHC, but this is the Fermi coupling, so this is this one knows from low energies really, so it's just muon decay, for example. So how much that happens, so you can extract that. And now we've seen in our standard model course that we know this leading order. So that's what sine squared theta W has to be. And we also know that G is this. Okay. And therefore we have a standard model prediction for something which is apparently completely unrelated, which is the coupling, the electromagnetic coupling at MZ. That's the prediction for it. We've got all our inputs from the above, but in terms of MZ and WGF, completely unrelated apparently, and therefore can check if this actually holds. So the standard model is an over-constrained system. Run that again. That's the real bottom line, and that's the basis of a lot of these precision tests, and particularly these electroweak precision tests. So we can stress test. And I've got a slide for you to have a look at offline, showing you some of the kind of things that go into these fits. Electroweak precision fits. So actually, can do this above his leading order, above relationships. They receive higher order electroweak corrections, just as you have to do it in QCD. It happens in the electroweak theory, but one can include them as well, and really do precision tests and parameterize your uncertainties and so on and so forth. And so far, everything looks consistent with the standard model. So there's many observables here, but two of relevance, very much of relevance for the LHC, are the W mass. Now you might think, well, so what? In the W mass, whatever the mass, you just measure the invariant mass of the decay products. I mean, why do I need all of this QCD or any of that for that? Well, exactly because a W decays to a lepton and a neutrino, and we don't measure the neutrino, so we can't reconstruct its mass directly. But what we can say is that very roughly, that the PT of the lepton, which we can measure, should be of order W mass over 2. It's only a leading order in the prediction, and if the rapidity of the lepton and the neutrino were 0, then it would be precisely MW over 2, but in general, one has to integrate over all the rapidities, and therefore it smears it out, and one goes to higher orders, and that smears it again. But one essentially ends up with a distribution that peaks there. And therefore, if we can predict d sigma dpt lepton precisely, we can extract MW, because all we do is we look at the data, we make a set of predictions, so-called templates for different values of the W mass, and we just see which one lines up with the data. And the more precisely you can predict these things, the better you can do it. But what is the prediction? We do it on the next slide. Well, it's this again, isn't it? Quark and an antiquark giving you a W. So we need to know the PDFs. These things can radiate gluons, so we need to know QCD corrections. Across all of the different phase space regions, we need to understand all of that. And that getting that under control is one of the key things at the LHC in terms of precision physics. So all of that QCD I've talked about really comes in there. Another nice one is the forward-backwards asymmetry, and I've got some slides also, again, to have a look offline showing that. So forward-backwards asymmetry. So now we are measuring the two leptons, the Z to lepton L plus, L minus, and here parity violation in the Z to fermion coupling induces an asymmetry in essentially the L minus decay angle theta with respect to the quark. Okay, so it's not symmetric. So we can measure that. We can get sensitivity in particular to things like sine squared theta W, which go into these electroweak precision tests, so testing the standard model. Well, how to measure? We certainly don't know we certainly can't reconstruct the quarks, where they're going, because of course they come from the proton. So again, it's telling you we need to know about PDFs. And indeed, you know, if these leptons are produced at zero rapidity, actually, we don't know from which proton the quark is coming, because it's coming equally from both colliding protons, and so this asymmetry gets washed out. But if we go to forward rapidities, then we know that valence quarks tend to dominate, and those tend to carry higher momentum fractions, and therefore one can say, in a probabilistic sense, that if the dilepton system is produced in the forward direction, in forward angles, if you like, that it's more likely that the quark comes from the corresponding proton moving in that direction. And with that, you can get out these extractions of sine squared theta W. But again, that relies on PDFs. It relies on understanding all of the QCD in the production process. What else? This is one final nice one to talk about, which is the Higgs and vacuum stability. So the Higgs potential, remember, went like this. And lambda is greater than naught, and therefore we have this minimum, and yeah, spontaneous symmetry breaking. So very good. But here's the point. As with all things, these things receive quantum corrections, and therefore they run with energy, just as alpha and alpha S do. Lambda varies with scale. In particular, the dominant contribution to this comes from the top quark. So remember, lambda now is the cubic Higgs self-coupling. So it's in particular due to dominant loop corrections. Let me write that down. So there's the tree level, and there's the loop. So that's the top loop. That's the Higgs as usual. Okay. So the first thing to say is that this lambda scale dependence is highly sensitive then to the top mass, because that affects exactly how this modifies the coupling. In fact, it's actually sensitive to the Higgs mass as well. So the correction to lambda, being very schematic here, the sort of size of the correction you would receive at any given energy scale would be proportional to that quartic in the mass, so very sensitive, as I say. And what you find is that actually for certain values of the top mass and the Higgs mass, which are pretty close to what they could actually be, suddenly the sign of this lambda can flip at sufficiently high energies. And if the sign of the lambda flips, we're no longer in a position where we have this stable vacuum where we live now, but rather something which has a completely different behavior. So indeed, let me perhaps show you quickly a slide to give you a flavor of that. One essentially goes from, one could imagine being in a metastable vacuum and actually tunneling through to the true vacuum, which can exist at higher energies, for example. And if that happens, well, just as this paper says, you get these bubbles which could potentially appear spontaneously, and once they've appeared, they'll start to grow and they'll absorb the whole universe. So in each of them, this is just from a paper, so in each of them, the transition happens locally in a small volume, nucleating a small bubble of the true vacuum. The bubble then starts to expand, reaching the speed of light very quickly and destroying everything in its way, which, yeah, actually escalated very quickly. And whether or not that happens, you can see the top plot there depends precisely on the Higgs mass. And you can see here that, and the top mass in particular, exactly where and when it happens, and if it happens, depends on the masses of the particles in your theory. So quite a lot of level of importance in working out what the top mass is. Now, what is the top mass? Well, again, it's not as simple as just measuring decay products, because that's just not how the top decays. I mean, in principle, it can decay completely hadronically. There's of course lots of uncertainties there. So how do we actually get the top quark mass out? Well, how do we produce this thing at the LHC? So think about TT bar production. There's your top quark pair producing gluon fusion. The top will decay, let's say, to a lepton, and that's going to be a B, so a B jet. Perhaps this one decays to a Q and an anti-Q, so that's going to be hadrons, more jets. That's a B jet. And everything that's going on in there, the gluon PDFs that produce it, the value of alpha S, higher order corrections, jet physics, you know, all of that. If you understand all of that, you can in principle compare your prediction with the data and get out a value of the top mass. And certainly that's an interesting way to do it. But alternatively, of course, measuring the Higgs properties themselves directly is, of course, very interesting as well. Okay, so we really are coming to the end. And I purposely haven't talked about BSM at all, because I think given the number of lectures we have, it's just not feasible to address it. But the point I kind of want to make here is that, you know, let's never forget that we're looking for BSM is, of course, one of the key driving factors behind collider physics. And there's, of course, a lot of interesting stuff that can be said about different BSM models and all of the different ways you can get at them. And that would take an entire other lecture course. But what I've tried to give you here is a flavor of the fact that because we're colliding protons and there's always QCD going on, there's a lot of interesting and important physics that one needs to understand. And if you're ever going to do those sort of collider physics searches, probes of BSM, let's say. I mean, I say one, of course, you know, if you're doing an analysis, that stuff, of course, could well be hidden in a black box somewhere, but it's still there. And it's only because of these sort of nice features of factorization and the fact of asymptotic freedom that we can ever do this. So it all relies on those non-trivial nice features at the end of the day. But again, looking for BSM is one of the key driving factors. And, you know, the real thing to remember here is that, yes, the standard model is so far doing great. But it's always worth remembering, you know, that it cannot be the final answer. So we've got matter, antimatter, asymmetry, which exists, and CP violation in the standard model isn't enough for that. Okay, we've got neutrino masses. How do they fit in? Gravity, the very fundamental level. How do we include that in our theory? Is it string theory? Is it something else? Maybe not something we can probe at the LHC, but it's worth pointing out. Dark matter very much could be something that we could, and which is again something which we pretty much know is out there and it's not in the standard model. Strong CP problem, which is the idea that there's a parameter that in principle one can include. There's no symmetry forbidding it in the case of QCD, which if it were there would have very important consequences experimentally, which we don't see. And so it's a complete mystery why this thing apparently is zero. And to get around that, you can introduce, for example, this thing called an axion, which we're actively looking for. So that's a more of a theoretical problem, if you like. You could just set it to zero by fiat, but yeah, it doesn't seem very nice. A hierarchy problem, the fact that the Higgs mass receives quantum corrections, which if you interpret them literally as corrections from some loops at the energy scale where the standard model theoretically expect to break down, so maybe the Planck scale, would drive it naturally to be very, very heavy, much heavier than it would actually observe it to be. Why has that not happened? And you know, why is the top mass over the electron mass of order 10 to the 5? There's even deeper questions than that. So not all of these necessarily can be answered by looking at the LHC, but certainly some of them can, and they can point us in the right directions. So lots of questions, not so far, so many answers, but of course that's an interesting situation to be in. And you know, using these tools of collider physics and phenomenology, which I've told you a little bit about, we can really exploit the LHC to hopefully shed some light on those issues. So I'll stop there. Thank you very much.